We'll move on to high-resolution spectroscopy, and the talk will be given by Matteo Brogi from University of Turin.
Thank you, Renu. Thank you, everybody. I'm really sorry I couldn't be there. From the looks of it, like it looks a fantastic workshop. So I'm sure I'm missing out. At least I know the lost iPhone wasn't mine. I've been asked to give like 25 minutes, a bit of an overview of what high-resolution spectroscopy is and what could be in the future. And I have to say the previous speakers really helped me out here because they introduce most of the concepts I'm going to touch on in much greater detail. So let's get straight to it. So I'll start by highlighting the differences. You've seen already some high-res and some low-res. So when you go to high-res, as you heard it about already, what you really do is to start resolving those bands. There low resolution appear as broadband variations of the spectrum into the individual lines. So these are the quantum mechanics transition Hannah was referring to. So what you can start doing is really recognizing which species is which, not by the broad variations, but by looking at each individual line and start matching it with models, with template line by line. For instance, by cross correlation, as Jason was already explaining before. But on the contrary of what direct imaging and high resolution does, in this case, for the majority of this talk, I'm not talking about separating spatially the planet from the star. So the planet is always buried into the photon noise of the star. So how do we go about it? How do we separate what comes from the planet and what comes from the star and our own atmosphere as well? Because high resolution spectroscopy at those levels of resolving power can only be done from the ground. Well, instead of using time resolution, as you saw in Hannah's talk and in Laura's talk, so instead of having a light curve, you use the Doppler resolution. So you let the planet move along the orbit. And since the spectrum is subject to a change in Doppler shift, you hope to detect that Doppler shift. So what I'm showing here on the right is a toy model in the sense that the color scheme has nothing to do with the actual absorption of emission in the exoplanet atmosphere on our own atmosphere, but the shifts are. So the signal that you see wobbling around as the planet moves around the orbit is at the right magnitude of a hot Jupiter around the solar type star. So we are talking about tens or hundreds of kilometers per second, which is well resolved. It can be resolved quite well by high resolution spectrographs. In contrast, if you know about stellar spectroscopy, when we look for a planet indirectly by looking at the motion of the parent star, we are talking about tens or hundreds of meters per second. And this difference of orders of magnitude is the mass ratio between the star and the planet. So what you can start doing by resolving the Doppler signature is really separating what comes from the planet and what comes from either our own planet, the Earth, or the star, which would be these vertical dark bands that you see in the figure. And you can do transmission spectroscopy almost exactly as Hannah explained before, but you can also do the exact spectroscopy, this time not looking at the secondary eclipse, but looking just before or after secondary eclipse, which also means you can do these same measurements also for planets that do not transit. And this has been done a number of times, especially in the early stages, and has led to mass and inclination estimates for some of the staple planets, like the very first discovered, including 51 Peg. That was the first one to be discovered around a solar type star. All right. In this slide, I just want to convey that there's a lot going on under the hood that I'm not going to talk about. This is about the data analysis. So the data analysis, what it does in a nutshell, is to use this Doppler separation between the signature of the exoplanet and any nuisance spectrum. It could be the Earth spectrum or the stellar spectrum. So in step one, what you do is to try to model these variations out. Everything is stationary in wavelength. And in step two, you divide through the model and you normalize those nuisance terms out. Which leads you to the central column. Obviously, if the planet and the star had equal flux ratio, this would work very well. But as I told you before, and as you know, the star is so much brighter than the planet that as a matter of fact, the planet stays buried into the noise of the star. So how do we go about that? We have to do something to enhance the planet signal, which is at this stage dominated by stellar photon noise. And as you heard in Jason's talk, one of the ways of going about it is actually doing cross-correlation. So we have a more or less noisy spectrum, which is in blue here, and you slide a model, what you think a good representation of your atmosphere is for various levels of radial velocity. And when the radial velocity matches between the two, you get a positive peak. And this is quite easy to understand in the case of a spectrum that is already quite good quality, like the one on the top. But as you can see, even in a spectrum where each individual line is deeply buried in the noise, which is more realistic with respect to what we can do nowadays, you can still get a peak at the right radial velocity. And perhaps if you look in the literature, what is strange is that these results in high-resolution spectroscopy are presented. Oh, sorry, I just wanted to say that this allows you to increase the signal-to-noise ratio, this cross-correlation, by the square root of the number of strong lines that you have available. If you look into the literature, you probably have seen that these detections of species are always presented in a two-dimensional space, which are essentially two velocities. One velocity is the systemic velocity, so it's the velocity of the system as a whole, and which will be on the horizontal axis on this plot. And the other velocity is the radial velocity semi-amplitude of the planet. So how fast the planet is moving around the orbit, projected onto the radial direction that comes towards the observer. So a detection is always claimed when the cross-correlation peak deviates significantly from the noise level, as you can see in this case of Tau B back in 2012. Okay, so what's the history? So the method actually started a long time ago, earlier even than space observations, but it took a while to kick off, and it's a combination of factors really. But the most important ones were the absence of a data analysis that will work on these type of data. And secondly, also the absence of proper spectrographs to test the methodology on. So for a while, nothing happened. Then there was the first phase in which carbon monoxide and water were detected. And then there was, say, an exploding phase in which many more molecular species were detected as recently. And that coincides with many more near-infrared spectrographs coming online. However, the infrared is just part of the game. There are also a dozen atoms detected, mostly in the optical. And I think what is neat is that we have mostly detected all the species that are thought to be carriers of carbon, nitrogen, and oxygen. And this has quite important consequences in order to be able to estimate the planet metallicity. And on the atomic side, what we know is that since atoms have higher opacity than molecules, we can probe higher up in the atmosphere. So the hope there is to actually start tracing also potentially atmospheric escape by looking at particular atoms. And I just put here like a list of references, like the first discoveries or claims of a certain species. But here I really want to start stressing first difference with low resolution spectroscopy. By the time HRCCS had started to detect all these species, that was it. It was a detection, whereas like a low resolution, as you have seen already, had already started to do comparison and measurement, or what basically translating those detection into a meaningful answer about the origin and evolution of exoplanets. So I'm going to show you first some of these detections, and then a bit critically, I'm gonna tell you what, in my opinion, needs to be the next step in the methodology. So for the optical, I could have picked many references, but this one is the first one that presented multiple atomic species in such a large amount. This is for the exoplanet Cal 9b, which is, by the way, the hottest exoplanet that we know to date. And this was done by optical high-resolution spectroscopy. And for atoms, really, this is not surprising that we detect all these species, especially for ultra-hot Jupiters. The notable exceptions are titanium and vanadium. They're quite hard to find. And the same stands for the molecular counterparts, so titanium oxide and vanadium oxide. So since these species are thought to condense out of the atmosphere quite easily at the temperatures between 1500 and 2000 K, that might be something there that we still miss in terms of modeling. And for the molecular species, I'm presenting also simultaneous detection, quite recent, of 6 molecular species. And I know some of you are working with ERS data and might start shouting at me because it doesn't look like JWST is showing too many of these species. And so this is actually a good environment, this workshop, and a good point to stress out one important difference. It is not easy to compare these high resolution observations straight out of the detections to JWST spectra. And the main reason is that it's not easy to understand what a detection means for the atmosphere. So for instance, I could have the sensitivity at high res to detect something that has a very low abundance in the atmosphere, so low in fact that it's visible at high res, but it does not show up in a James Webb Space Telescope spectrum. So really, in order to make the comparison fair and also informative, and perhaps even highlight some of the limitations of this technique, we really need to move beyond detecting and towards measuring. So what does it mean? You've seen this spectrum from Hannah, the one on the left already. This is what space observations can deliver, right? This is fantastic. You see a spectrum, this is a transmission spectrum. You see all the wiggles. You can directly relate those to the presence of certain species. You can compare it to models at various levels of complexity, as Hannah already hinted to, but you've got ground truth to refer to. In high res, on the contrary, you've got a level of correlation. So you never see the spectrum, at least for these hot Jupiters, or these like closing exoplanets. You only see whether a model is able to pull out a correlation with the data. So a model spectrum is able to give you a correlation with the data. So for a long time, it has been quite hard to assess the goodness of fit and even compare models. So which model is actually fitting the data better. And this basically was only solved a few years ago, when finally we found a way to translate a cross-correlation measurement, a correlation measurement, into a likelihood measurement. So we could go into territory of statistical analysis, Bayesian inference, something you'll hear about also from Mike Line later this week. And but also here, I want to continue to be a bit skeptical about this high res. I'm playing the game of somebody not working in high res, because you can use this and you can start exploring algorithm models, right? You can say, what happens if I explore algorithm models in thermochemical equilibrium? And here again, it's the same planet I presented earlier. And you could start having some good constraints on C2A ratio, metallicity. You lose, of course, the ability to do the inference about individual species, because in this case, all the species coadd together to give you the signal. However, even here, you are on a grid, so that your interpretation might change if you start to account for the muting effect of clouds or disequilibrium processes. So even this is not a fair and probably meaningful comparison to an actual space spectrum. So really, in my opinion, the real way around it, like to have a fair comparison in this decade and beyond between space and ground observations, is like to explore all the parameters that we need, that we think are relevant at once, which basically is done similarly to what is done at low res via Bayesian retrievals. And really here, Mike Line will explain what these are, I believe, later today. So we actually, I'm presenting here perhaps the best result that we have so far from high resolution by Bayesian retrievals. This is also a hot Jupiter. It's a normal hot Jupiter, nothing, you have seen this from JWST already, the emission spectrum before. This is 177 AB. We found only 2 species here, carbon monoxide and water. Plus possibly a hint of the isotope log13CO. Despite we explore a model parameter that has 16 parameters, 7 species, 6 for the temperature pressure profile, the 2 velocities, one scaling factor. So this really simplified things in a way and allowed us to actually measure the abundances of water and CO with 10% precision, right? 0.1 dex. Which was obviously unexpected, completely unprecedented from high resolution, but even from space observations, it's quite high quality data. And you can start with this quality to start populating the mass metallicity relation that you already saw from Hannah's talk. I'm not focusing too much here about the possible meaning of this measurement, but I would just like to showcase what's the precision of the data you can get when everything goes well. So the other thing that I think is quite key is to assess whether these predictions are robust. So if you take high resolution spectroscopy by itself and you try to predict what the JWST spectrum will look like, this has been done and it's been published already. You see in the case of 177 AB, the prediction actually quite remarkably good without doing anything to that prediction. So this is like the posteriors. This is the Bayesian analysis straight from Igreen spectra and extended to the JWST spectral range. And as you can see, it agrees quite well. So I think what it means is that there's really good potential, at least from the emission spectroscopy side, to jointly analyze space and ground spectroscopy. What's the catch here? And I need to be very careful about this. The catch is that since you need to model and remove telluric lines, you are somewhat limited to very bright stars. And very bright for us means K magnitude less or equal than 10. There might be ways around it if you find other ways of modeling the tellurics, but so far this is quite a limit. Which means with a few hours of telescope time, I'm talking about 5 hours, combining transmission and emission spectroscopy, you've got about 50 targets, which are easy to do. By the way, those of you interested might want to know that most of the data for these 50 targets is already in archives, and most of it is already public. It's just it has been used for other purposes, but it is in telescope archives. So if you're interested, there's a lot of data to play around with. And the main requirements is due to the fact that you need, like, per spectral channel, you need quite a lot of signal to noise. That 50 is quite conservative. You can go a bit lower than that, but not too much lower than, say, 10, 20 per spectral channel, to be fair. So this was about the molecules. What happens to the optical, all the atomic species detected? Well, even here recently, Sid Gandhi made a comparative study of 6 ultra-hot Jupiters. And as you can see, like, here's all the abundances relative to hydrogen that he was able to measure. The striking, perhaps not too much, but the interesting result was that different atoms leads to different metallicity if you take them as tracers of metallicity. And calcium and iron seems to be the most reliable across the most constant across the sample. And also iron seems to agree with the predicted abundance in equilibrium. So iron is once again probably a good probe of metallicity for the planet. So if you do that, and you start repopulating the same mass metallicity diagram, as you can see now, there's not only just one point that is below the solar system trend, but all these ultra-hot Jupiters that I show you on the left turned out to be systematically slightly below the solar system relation. So as you can see, this is fantastic. What you can do with that precision compared to, you know, the big error bars of previous measurements, which were entirely relying on HST. Is really to tighten up the relation if a relation exists. And this is really working well in synergy with JWST, because JWST should also deliver measurements with this precision consistently. So, you know, this is a clear synergy there. Okay, let me quickly scan through another quite unique aspect of high-resolution spectroscopy, which is tackling possible winds or rotation of exoplanets. So either you have the planet bulk rotation, so a Doppler shifted, a blue shifted and red shifted hemisphere, or you have an equatorial jet stream, so like something that is super rotating in the deep atmosphere. And I apologize to the GCM people there because this is an observer perspective on it. So please bear with me. In transmission, you might have high altitude, blue shifted winds coming towards you. You may have the hotter approaching terminator of the planet as a stronger signal than the cooler receding half terminator. And even in emission, you can have the hotter approaching day side counts more than the cooler receding night side of the planet. All these effects are predicted to produce kilometer per second variations in the Doppler shift. And these are well detectable at high res. And in fact, such effects have been sought after in the 10, 15 years of the methodology. And so far, most of the observational evidence comes from transmission spectroscopy, mostly from iron, sodium, and in the infrared from the combination of carbon monoxide and water. And very quickly, this is like the very first detection with this methodology back in 2010 by Snellen et al. Already highlighted a possible blue shift, although it was only a marginal effect. Then in 2015, Loudon and Wheatley demonstrated that looking at sodium, you could separate the two half terminators of the planet that had different dynamics. I myself tried to do the same with the CO and water lines for the same planet. And it turned out that I could constrain the planet rotation to be synchronously rotating. And perhaps the one that will resonate, at least with some of you the most, is the more recent detection of an asymmetric iron signal in transit for Cal9b. Okay, where do we go from here? I just wanted to give you a little bit of perspective. It is definitely the case that we will move from towards those planets around M-dwarf stars, not only because these are the most common stars in the neighborhood, but also because being smaller and cooler than the sun, it means that in comparison to the exoplanet signal, all the contrasts are enhanced. So for instance, if you can detect a transit of a Jupiter-sized or a planet around a solar-type star, you can detect a 2 Earth radii planet around M5 star. And it's same for thermal emission. If you can detect a hot Jupiter emitting around a solar-type star, you can detect a warm Neptune emitting around M5 star with no change on instrumentation, right? This is just a scaling factor exercise. And the other neat thing is that we are really starting to become complete in what we know about planets around M-dwarf stars. In fact, we already know, probably with all probability, the closest transiting system to the Earth around M-dwarfs. And we cannot get any closer than that. We already know that there's 2 planets, possibly one for sure, the second one very likely around the closest star to the Earth. So, you know, like this sample is a complete sample and it will be very soon and for the foreseeable future. So there's a lot of work to do with this. So what can we do with that? One thing that we could do, and some groups ventured into, is to study whether we could detect oxygen. There were some questions in the Q&A before whether oxygen could be detected. Well, some people try to look at that. And the nice thing is, like, if you look at Earth around an M5 star, the signal of oxygen at 0.76 micron around an M5 star is only 1/3 of the signal of CO around tau Bootle speed we have clearly detected. So what's the catch? Why aren't we doing it now? Well, the catch is that the star is at least 6 magnitudes fainter than tau Boo, probably more. So you really need to crank up your mirror size to do this. And the jury is still open, but it seems you need at least 30 transits, which will amount over, I mean, every time a transit is observable, you would have to accumulate data for 3 years before hoping for a detection. And this is if the radio velocity separation between the Earth spectrum and the proximal B spectrum is suitable, and also if you can ideally remove all the telluric lines, so suppress any spurious signatures. In fact, if you actually go a little bit deeper and you start simulating this with current observational technique, the situation isn't quite positive anymore. So there was a recent paper that was showing that actually in the infrared, when you account for the analysis, the species that are probably easier to observe are methane and CO2. But the data analysis makes the observation of other species quite a lot harder. So in fact, this is the only result that I'm showing you from my group that is still in prep. But we obtained the same. So if you consider the whole near infrared spectrum at once, you could just need 15 transit if tellurics can be removed, like ideally, to detect the spectrum. But when you apply current telluric removal, the signal is essentially canceled out aggressively by the data analysis. So what this means is that the ELT can detect Earth-like exoplanets around M-dwarf stars, but likely not with the current analysis techniques. So we need more. So my time is off. So I'm not going to talk about combination of high resolution spectroscopy and high contrast imaging, but I'm going to just jump to the last slide, which shows you that the ELT is well under construction, is approximately halfway through as a structure. And my checklist for high resolution spectroscopy is that the low hanging fruit is to continue to detect species, but I don't think it's the most compelling science. It's hard to compare to space observations. It's hard to give a meaning to the exoplanet atmosphere. I think the science that we should be doing right now is really measuring in a Bayesian way the composition of these exoplanets and combine these observations with what JWST is providing. And for the future, I think we should learn from the JWST community, who's come together and has created software predictions so that JWST, when it was launched, was a machine ready to be used. It is not the same for the ELT. So there's a lot of community work to do. And I'm just leaving here a few things that we could be doing in the next few years to prepare for the ELT. And I'll take any questions. Thank you.
Hello, for ground-based high-resolution spectroscopy, how big of a problem does telluric corrections pose to getting good, clean data out of that? And what role does synthetic telluric corrections play in addressing that?
Yeah, the main limitation at the moment is that with the telluric removal only works in the way most of the people do if the planet is moving fast along the orbit. So for planets that are slowly moving, including these temperate exoplanets, direct modeling is the only way forward, and we are still behind on that. So we can do like the 0.5%, the fraction of a percent, like compared to the original depth of the line, but that's not enough. It's still like 10 to 100 times stronger than the exoplanet signal. So you can try aggressive masking, but there's work to be done to directly model the telluric lines indeed.
Let's take a question from online audience.
So this question asking, how would we expect disequilibrium chemistry like dynamical mixing or photochemistry affect high resolution spectra, and to what significance?
Yeah, it's a good question. Detecting species seems to be relatively easy, but the problem is, like, for instance, if you have effects like photochemistry, which would change the abundances at different levels in the atmosphere, that could be tied to dynamical effects as well. And currently, as much as we like running our 1D retrievals, we have no way of actually telling the retrieval code that one molecule is moving differently from another molecule. So in terms of coding the signals coherently, that could be a big problem if on top of the disequilibrium chemistry, we also have a gradient in, say, the velocity, the Doppler velocities that we measure for those species. Even at the kilometer per second level, that could be a big problem. But there's also an opportunity because this minor species seems to be detectable to a high level of sensitivity at high res than it is at low res when they are smoothed out and broadened and perhaps hidden under the absorption of the other species.
Any other questions? Right, if not,